Okay, so in this video, it's continuation of evaluating limits. And now we're going to look at some limits where we end up with infinity involved in one way or another. So in the first one, we're looking at what happens when you get close to 3, but from the right side of 3. So if we think about what this does, limit as x goes to 3 from the right side, 2x over x minus 3. What we used to do is a sign chart, but now we can just kind of look at it and analyze it. If I plug in a number just bigger than 3 right here, the top is just bigger than 6. And if I plug in a number really close to 3 but just bigger than 3 on the bottom, I'm going to get a number, so a number just right around 6. But then on the bottom, it's going to be a very tiny number. And in this case, since it's going to be a little bit bigger than 3, that's going to be a tiny positive number on the bottom. And anytime I take some constant and some positive constant divided by a really tiny positive number, that thing's going to shoot off to positive infinity. So this actually tells me that, at least at this point on the graph, 3, from the right side, this thing's going up to infinity like that. Let's look at what happens on the other side as 3 goes to, as we get close to 3, but from the left side. So let me write it down here. That means that I'm plugging in a number very close to 3, but a little less than 3 there and there. That's what I want to see what happens on the picture. And so that means that I get a number really, really close to 6 divided by something just less than 3 right here. So this becomes a tiny negative number. Right? Some tiny negative number like 0.00001. And the smaller that number gets, the closer that whole thing turns into negative infinity. So that means on this picture, you've got something like here it's going up like that. Here it would be going down like this around 3. Okay, let's take a look at the third problem. What happens as x gets really, really big? Right? 2x over x minus 3. Well, there are a couple ways of doing this. One way is the algebraic way to do this would be actually to come up with an equivalent function like this one. Right? The problem with the original function, if you ignore this, right, just ignore that for a second. The problem with the original function is that you can't necessarily just plug in infinity because you have infinity over infinity, and I have no idea what that equals. It turns out it doesn't have to equal 1. So if I do this, then I'm going to end up with the limit as x goes to infinity of 2 over 1 minus 3 over x. And now if you plugged in infinity, you get 2 on top and 1 minus 0 on the bottom. So you get 2 over 1 minus 0, which is 2. The other way of doing this, it's kind of a shortcut in a sense, is to look at the functions. Now this only works for infinite limits. Way out at infinity, only certain terms matter in this function. The 2x dominates the top because there's nothing else on top. But the x term, if I'm doing infinity minus 3, well, that 3 doesn't really do anything. So this is the dominant terms approach. And when I do that, I can just look at dominant term on top over dominant term on bottom. That graph's messed up at 0, but I don't care about what happens at 0. Everywhere else it equals 2. Okay, so this method is the dominant terms approach. Whereas the other one, this one up here, would be a more algebraic approach. Okay, let's look at number 4. Number 4 is actually asking the same thing as 3, but negative infinity. Well, it turns out all of these up here, if I just put a negative infinity, nothing actually changes in this case. The same terms are still dominating, and you still get 2 out of it. So this thing ends up equaling 2 as well. And what each one of these, this actually tells me, since it equals 2, that there's a horizontal asymptote of y equals 2 on the right side. This tells me a horizontal asymptote of y equals 2 on the left side of the graph. Let's look at 5. Okay. So 5, I've got this limit of this kind of odd looking thing, a linear plus a trig over a linear. So let's simplify it a little bit. Let's see what we can come up with. Remember, I can write this where I split up the fraction. So it's going to be 5x over x plus sine x over x. And remember, the sum of the limits is really, or the limit of the sum is really the sum of each individual limit. The limit of 5x over x everywhere, that's always just 5 except at 0, but it doesn't matter what happens at 0. It matters what happens at far out, huge numbers. And then if I take the limit of sine x over x, well, sine x over x, remember that's one of the important ones that looks like this. So way out at infinity, this thing turns into 0. So it's 5 plus 0 equals 5. You could also take a dominant terms approach to this one too. The dominant term on top, way out at infinity, well, this just keeps bouncing back and forth between -1 and 1, whereas that totally takes over. So I just do the 5x on top divided by the x on bottom, and you get 5. Okay, this one on the bottom here. So this one I would almost certainly go the dominant terms approach. This one we can turn into the limit as x goes to infinity. Since it's an infinite limit, the only term on the top that really matters is 2x cubed. And the term on the bottom that matters is the square root of 4x squared. Now this graph is definitely messed up when x is 0, because I can't divide by 0. So let's see if we can come up with a function that isn't messed up at 0, but it's equivalent to this function everywhere else. So the top is 2x cubed. The bottom, I can take out the 4 as a 2. The x squared, square root of x squared, you got to be a little careful. That is not just x. It could be, it's really a fancy way of saying absolute value of x, right? So, for example, like if I said square root of -3 squared, that is not -3. That's got to be 3, right? Because it's really saying what's the square root of 9 under here. And the square root of 9 is not -3. I can't take the square root of negative and get a real number. So really what you want to do is you want to train yourself to think this way. For absolute value of x, it's also square root of x squared. So this is this. So I can cancel those 2's, and I've got the limit as x goes to infinity of x squared over the absolute value of x. Well, since x is going to infinity, it's a positive number. So it's a positive number squared over one version of that positive number. So this is just going to turn into limit as x goes to infinity. So everything's positive over here, so this just turns into x, and then that just turns into infinity. So this thing still shoots off to infinity regardless. Okay, hope that helps. Let me think. Oh, actually, let's just do the rest of it. End behavior. Okay, so if I have two functions, f and g, so let's say f looks like this, f. Here, I'll do this. So let's say that's f. And I have some other function g, and let's say g just looks a little simpler. G does this. So this one's g, and f is the one below it. Well, if f and g look like each other the further out I go here, then really they have the same end behavior. And the way that you would describe that is you'd say way out as x goes to infinity, f of x looks a lot like g of x. So if I were to divide the two of them, way out at infinity, they ought to be the same. They should just give me 1 back, right? So that's the way that you actually prove that f and g have the same end behavior on the right side. So in our problem, we've got an f, we've got a g, and we want to show that they have the same end behavior, but on the left side. So really, I'm going to write this instead. Left side just means negative infinity. But if they look the same, right, if whatever one function looks like the other one, well then when I divide one by the other, I should still get 1. So f of x over g of x, we want to see if that equals 1. So let's write out our functions. 3x to the 5th minus 5x cubed plus 2x, all divided by 3x to the 5th. Well, we're looking at an infinite limit here. So you can do 2 things. One is you could divide by 1 over x to the 5th, and multiply by 1 over x to the 5th divided by itself, and then that'll actually turn into this. So you get 3 minus 5 over x squared plus 2 over x to the 4th all over 3. And now if you actually plug in negative infinity, this turns into 0 and that turns into 0, and you're left with 1, which is good because we want 1. The other route you could have taken instead of this route would have been to do this instead from here. You could have just said, well, let's take the dominant terms. Dominant term on top, 3x to the 5th. Dominant term on the bottom, 3x to the 5th. So those guys are exactly the same everywhere. And so the ratio of them is going to be 1. So that proves end behavior is the same on the left side. Oops, sorry, negative infinity there. Okay, let's look at the second example. Show that f of x equals x plus e to the negative x, and g of x equals x have the same end behavior on the right. It turns out that this function right here, it actually looks like e to the negative x on this side, and then shortly after you get to the y-axis, it looks like y equals x on the other side. So you can tell that the functions are sort of dominating certain sides of the equation. So there's a dominant term for the left and a different dominant term for the right. And we're just looking at the right side. The right side means we want to see what happens when we take this ratio as x goes to infinity. Okay, so we're going to look at f of x over g of x and hope that this turns into 1. So let's write them out. X goes to infinity, x plus e to the negative x all over x. And let's break that up to make it a little bit simpler. X goes to infinity, x over x plus, let's go, yeah, e to the negative x over x. Well, this is 1 everywhere except at 0. And since I only care about really big numbers, I can just turn it into 1. Plus, and then e to the negative x is like e to the x in the denominator. If I plug in infinity here, and I plug in infinity there, or a really big number, let's say, then you get a massive number down here, which 1 over that is essentially 0, so we just get 1 out of this, which is great. That's what we want. Okay, I hope that helps.